Good afternoon and welcome to NASA's Kennedy Space Center and the Forward Osmosis Bag Experiment Demonstration. Joining us today are Dr. Howard Levine, NASA Project Scientist, and Monica Soler, Project Engineer with Kinetic North America. We'll begin with some opening statements and then go into the demonstration.
So we'd like to show to you a tech demo project that's flying on the shuttle Atlantis this Friday. All right, it's what we call the forward osmosis bag. So think of it as a bag within a bag. And the outer bag you can introduce dirty water or water that cannot be drunk by the astronauts. On the interior, the inner clean bag, we introduce a high sugar solution concentrate. And just by osmosis, it cleans the water. It pulls the water through a semi-permeable membrane, selectively excludes elements, compounds, bacteria, viral particles that are not desirable. And you end up with a sports drink that maybe 4 to 6 hours later can be drunk by the crew members. This technology was developed at Ames Research Center, and it was licensed to a company, Hydration Corporation in Oregon. And they went through the SBIR, Small Business Innovative Research Program, to commercialize it. And they developed this product, which is for hikers, so that hikers out in the wild can put this into a stream, and water that may not be suitable for parasites, or suitable for parasites but not for drinking, can be cleaned in this way. There's also a version of this that has been modified for the Department of Defense, for soldiers in the field. The Coast Guard has also developed a version for salt water to make salt water drinkable. So the project will be flying on Friday. We're going to be, first we had to modify the bag. So this commercial product is not flight rated, as we say. It's has materials that are don't meet the stringent flight requirements of the International Space Station. So we created a flight version that has the proper materials. And Monica is going to go through a demonstration of how the crew members will load it up, both the dirty side and the clean side. And in the experiment, we're going to be flying 6 of these bags, 3 of which will be manually mixed by the crew, and 3 of which will not be. So we'll be seeing whether there's a requirement for them to be manually mixed or not.
So what we have here, what we'll be flying on Friday, we're actually going to be flying 7 of these forward osmosis kits. They're made out of Nomex, and inside of the kit it's going to hold a forward osmosis bag, an osmotic concentrate syringe, forward osmosis sampling syringe, and the input storage bag. And each kit's going to have a letter identifier, A, B, C, D, and so on, for the crew member to associate with. So as Howard was saying, we modified the commercially available off-the-shelf product and changed the materials from PVC to polyethylene for flammability purposes. And we also changed the ports to self-sealing quick disconnect ports for leakage purposes. You can imagine trying to pour in some water into one of these big red ports in microgravity. You'll have water flying everywhere. We also have your standard 60 milliliter syringe, which is going to hold fructose and glucose syrups in deionized water. As Howard had mentioned, it's going to be injected into the inner chamber of the forward osmosis bag. The sampling syringe is an identical version of the osmotic concentrate syringe, which will be pulling a 60 milliliter sample approximately 6 hours after each bag is induced. And the input storage bag holds 500 milliliters of potassium chloride and a methyl blue dye, which is your typical food coloring over-the-counter dye. And both of these items will be launched preloaded, and all of the lab work is being done at the Space Life Science Lab here at Kennedy Space Center. So to begin the initiation, the crew member is going to transfer all of the liquid from the input storage bag into the outer chamber of the forward osmosis bag using this forward osmosis pump syringe. So I'm going to rotate this to make it a little easier. So the crew member will ensure that the check valve that we have here is in the off position towards the forward osmosis bag. The Velcro that we have on the input storage bag is used to assist the crew member in pushing all the liquid towards the outlet of the input storage bag. So they can roll the bag just like that, and they're able to get all the liquid towards the outlet. And they'll be pulling liquid into the forward osmosis pump syringe, just like this. And then once they have it approximately full, they're going to move the check valve in the off direction of the input storage bag and slowly inject the forward osmosis bag with the dirty water. Now this cycle should take up to about 8 cycles for the crew member to get as much water as they can out of the input storage bag. So I'll go through this quickly. So as the water lessens, they'll keep rolling the bag using the Velcro to pull the dirty solution. Now the purpose of the methyl blue dye is to wet the membrane. It's to dye the membrane. So when the forward osmosis bags are returned for a post-flight analysis, we're going to be able to dissect the forward osmosis bag and see how the liquid wetted the membrane, whether or not it was a uniform wetting or if it was splotchy. We'll do a couple more pulls. And then once they've gotten as much liquid out of the input storage bag as they possibly can, they'll use a dry wipe, which they already have up there, just to make sure that there's no spots that come out, to disconnect the QDs from the input storage bag and the forward osmosis bag. So as you can see, all the liquid is on the outer chamber of the forward osmosis bag. Then they're gonna come and grab the osmotic concentrate syringe and inject the osmotic concentrate to the inner chamber of the forward osmosis bag. And the osmotic concentrate is the driver for the water to pass through the membrane. So the higher concentrated liquid pulls the potable water through the membrane. So once they're done with that, they'll disconnect. And as Howard said, 3 of the 6 bags are going to be hand manipulated. So hand shaken for approximately 2 hours. And this is just to compare whether or not mechanically inducing the bags will actually increase the flux rate of the water moving through the membrane, or if 2 minutes, approximately 2 minutes, yeah. So once they're complete with the initiation and the mixing of the bags, then they're going to restow them back into this forward osmosis kits and back into the storage mid-deck locker. And approximately 6 hours after this is done, they're going to come back and they're going to remove a 60 milliliter sample from the inner chamber of the bag using this forward osmosis sampling syringe. Very similar to the way we did with the osmotic concentrate syringe. They're just going to connect it and remove the 60 milliliter sample. I won't remove a sample right now just because there's only been a couple minutes since I've actually initiated the bag, so you probably won't see much of anything. And then they're going to restow everything back into the forward osmosis kit and back into the locker for return. All operations are going to occur within 2 days of landing, and all the post-flight analysis will be done here at the Space Life Science Lab at Kennedy Space Center. So.
And
So the key part of the science is 6 hours later, when the crew member goes and withdraws the 60 milliliter sample, you saw that this osmotic concentrate is yellow. Okay, it has a dye in it, a fluorescein dye. The sample that we collect will be diluted based on the water that's passed through the membrane. All right, so this is our microgravity sample. This is the most important sample of the whole experiment. And we'll be able to run this through a spectrophotometer post-flight and get an idea of the flux rate of the water passage through the semi-permeable membrane based on the dilution of this dye. This other blue dye, as Monica said, is to get an idea of the distribution of the water in microgravity on the semi-permeable membrane.
Okay, and now we'll take questions. Please state your name and affiliation and wait for the microphone.
Jim Siegel, Celebration Independent newspaper. So let me get this straight. Nobody's going to drink anything of that's been sampled here or experimented with on this flight, correct?
That's correct.
And could you describe a little bit about what this would replace if it was to be used on the space shuttle or the International Space Station in a little bit of detail, and how large would something like that have to be on the space shuttle or the space station in order to do that?
So we think of this primarily as an emergency contingency water system. So in the event that one of the normal physical chemical means of producing potable water went down, this could be used in an emergency situation. It could also be used in the future as part of an EVA, extra vehicle activity suit. Some of you may be science fiction fans. You may have read the Dune series with the Fremen on Arrakis, and they had still suits. Well, this could be almost a first step towards recapturing the humidity from our sweat, from our breath, even from our urine, and recycling it and making it drinkable. So mostly, I guess, to answer your question, as an emergency situation, it's not meant to be a day-to-day water generation device. But it could also be used when the crew comes back on a capsule and they land in the ocean. It could be filled with seawater and potable, drinkable, a sports drink kind of product could be made that way as well.
And just to add to that, this is actually phase 1 of the forward osmosis bag. So we're using this technology demonstration to demonstrate the technology of the membrane in microgravity. So we've already been accepted as a SDTO or XDTO for FOB phase 2, so that we would be able to take more samples at an hourly interval and get a better curve of the flux rate as the water passes through the membrane. So this is pretty much just demonstrating the technology of the membrane for this particular flight.
And the key point there is that it's necessary to elevate the technology readiness level of this technology and demonstrate that it functions in a microgravity environment. And that's really the main purpose of what we're trying to do. And once we demonstrate that it does indeed function in microgravity as it does on Earth, then the program can take it and plan on using this technology in future endeavors.
Okay. Ken, you have a question?
Yes. Hi, Ken Kramer from Spaceflight Magazine. Describe a little bit, the shuttle astronauts will do this, not the ISS astronauts. And when you do bring it up as an emergency situation, yeah, that's what I was wondering. How many bags would you bring up, and has anything like this been flown before? Thank you.
Well, I'll take the first couple of questions. Yes, this is a sortie mission. So a sortie payload meaning that it will be launched and returned from on the shuttle. It will not cross over onto the space station. So we have one of the U.S. crew members, actually Rex Wellheim, will be conducting the experiment 2 days before they're returning. And what was the second question?
Has anything been flown like this before? And how many units would you bring up to the ISS?
So no, this has not been flown before. And the number that would be brought up really that's a programmatic decision, but if you think of it, we spend quite a bit of money bringing water up to the International Space Station. There are contingency water container bags that are brought up. They contain about 43 liters of water. They're stowed. They have a certain lifetime after which they're no longer rated for drinking. These could be used to recertify those expired waters as a potable drink. Again, it doesn't produce water, but it produces a sports drink kind of a product.
And as an example for the post-splashdown, I believe each astronaut gets 2 gallons of water as they're waiting for a boat to come and pick them up. And so if you're able to just send a pouch per astronaut, you're reducing mass and volume that's going to be on the orbiter when they're returning. And each bag is able to be used up to 10 times. So you're able to recycle the bag up to 10 times.
So let me elaborate a little bit. So you saw that each bag can purify, let's say, 1 liter of water over the course of 4 to 6 hours. Over the course of 1 day, that would be 4 uses. And for most applications, the bags could be used up to 10 days in duration. So 10 days, using the maximum rate 4 times a day would be 40 times. It's all dependent on what you're introducing into them, but up to 40 times the bags could be used. And if you think of that, that's 40 liters of a drinkable solution. 40 liters, about 4 liters to a gallon, that's about 10 gallons. Each gallon of water is about a little bit more than 8 pounds. So, and if you think about $10,000 per pound for launch costs, that's a conservative figure. There could be quite a bit of a savings.
Just one last quick question. Can they be built larger?
Yes. Mm-hmm. This is really, an individual size unit, developed mostly for, commercial applications.
Okay, right here.
Jim Siegel from the Celebration Independent newspaper again. I think you mentioned that is commercially available now. And so 2 questions. One, if someone wanted to buy that today, how would they do it? Is there a website or something like that? And secondly, the forward osmosis bag. I assume you've done some testing here on Earth before you're doing this. So has anyone actually drunk the liquid that came out of that here on Earth, and are they still living?
Well, to answer your first question, yes, these are available, as are the CPAC and the Hydro Pack. The Hydro Pack has actually been used for hurricane and earthquake relief. Hydration Technologies has sent these over to Haiti for earthquake relief. And yes, their website is htiwater.com, tiwater.com, and you're able to purchase all of their products on their website. And your follow-up question, yes, in order to manifest a payload, we have to go through a whole payload integration process where we verify the science on using a science verification test, where we kind of use a prototype component of the hardware, but just to verify that the science would work. And we do it in our orbiter environmental simulator chamber, which actually follows one of the temperature profiles of the shuttle. And then once we verify that the science works, then we move on and prepare for a payload verification test, which is where we actually use the flight hardware and the science to verify that everything will work properly. And no, nobody has, to my knowledge, has drank anything yet, but we are able to produce the nutrients. I believe you can change the nutrients in the osmotic concentrate to fit any kind of nutrient profile that the crew members would need to nourish themselves and get it FDA approved. But
we did have some Japanese, a TV team from Japan, and they drank it a little bit. We advised them not to, but they did. And I saw a guy outside,
And
he's still walking around. Yeah.
And they said it just tasted like a sweet Gatorade sports drink. And the commercial product, if you were to purchase it, also the drinkable product would be a lemon, lime, orange. You can get any flavor that you want, pretty much. And it just tastes like a sweet sports drink.
But as part of our verification pre-flight tests, we did verify, we introduced, for instance, known concentrations of bacteria on the dirty side, and we confirmed the manufacturer's specifications that there's 99.9999% rejection of the bacteria by the semi-permeable membrane. There's also 99.99% rejection of viral particles. Similar levels for parasites and cysts of different types.
And the great thing about forward osmosis, you don't need any electrical, mechanical, any kind of equipment to use it. The membrane works on its own, and it's low mass, low volume, no power required, so it's a very ideal spaceflight application.
Okay, we have a question right here.
Sure. Pete Crowe, Zane Harbor Productions in Studio City, California. Two questions here. One, we visited briefly here. I believe you said about 80% you can recover. And then the second question is, will further testing be necessary, or you expect that this will be ready to fly on a operational basis following the end of STS-135?
We don't think that there's an immediate need for this on station. The program could fly them as is, the flight-rated versions. What we're trying to do is to get follow-up flights to further define the characteristics of the bag in a more precise way. We view this first flight as really getting over the barrier of elevating the technology relevance level and to demonstrate that it works in microgravity. But we could do quite a bit more in terms of studying the flux rates in a more scientifically rigorous fashion. But there could be some that are flown at any time after this demonstration. We're not aware of the program wanting to do that at this time.
Are there any further questions? Okay, right here.
Hi, Mike Burke, Voice of America. I just wondered what sort of potential might this experiment have for people who don't have access on Earth to clean water?
Well, just to further go on about the hurricane relief, I actually have their HTI's product, the Hydro Pack, in my hurricane relief package at home, and it's similar to a Capri Sun, but the sugar is already preloaded into a pouch, and you can just have a bucket of rain runoff or any kind of runoff water and stick the pouch in the bucket, and after about 4 to 6 hours of activation, then you can just stick a straw on it and drink it like a Capri Sun. So it is available for anybody to use for any kind of hurricane relief or earthquake relief or everyday use, actually.
Countries without clean water, will that have a potential feature to help that?
Well, it may not be the way that you would want to go for the primary generation of water. There are alternative implementations of the technology that aren't so much bags within a bag, but pumping devices that you can pump water through it, and the water that comes out is cleaner than what was introduced. So there's other implementations that I think would be more relevant for that, but based on the same technology.
And Hydration Technologies actually does do a lot of work in third world countries. They go over and they actually try to implement some water recycling systems using the forward osmosis technology. So that they do currently go overseas into third world countries and help them implement into little cities and villages, which you can find further information on their website, but they do.
Okay, I believe we have a follow-up front.
Jim Siegel again from the Celebration Independent newspaper. My readers are interested in the spin-off benefits of space exploration onto what's going on Earth today. So in this case, we have existing earthbound technology being applied to space. So can you see some learnings coming back to earthbound applications from the experiment that's going to be done here on Atlantis? Refining the technology or something like that.
Mm-hmm. Well, there has been quite a bit of research that's been done on Earth that has gone into optimizing the design for Earth-based applications. It's conceivable that we may learn something, and part of the reason we're flying is to see how does the membrane operate in microgravity without convection-based buoyancy, without some physical concentration mechanisms that are occurring on Earth or at decreased levels. So it's possible that the fundamental knowledge that's generated by this spaceflight experiment, which will be done in microgravity as opposed to 1G, might produce some enlightenment that could be used in Earth-based applications in the future.
Okay, any further questions? One more here.
Hi, Ken Kramer, Spaceflight Magazine. Can you talk about what's the total weight? It seems pretty light. And has this possibly been tested in these short-term suborbital flights at all, where you get microgravity for a few minutes?
So I believe each of these bags is on the order of 300 grams. Okay, so relatively lightweight. The problem with doing the Earth-based microgravity analogs, and there's two of those that I think you're referring to. One is the parabolic flight series, in which you get on the order of 20-25 seconds of microgravity interspersed with 2G and 1G. That would be very difficult because it's not long enough to get significant results. The other category, which is the new emerging suborbital industry that we're all looking forward to, there you can get somewhere between, or the promise is to get somewhere between 2 and 5 minutes of microgravity. It's still probably short for this implementation, but usually what you do is you design a different sized bag or whatever your hardware is that you're testing so that you could get significant results. So it wouldn't be these size bags, but we could scale them down so that we could get some interesting results from those implementations.
What is the weight of the whole system?
The whole payload weighs approximately 6.3 kilos, so about, 12, 14 pounds. And it's going to fill up approximately 2/3 of a mid-deck locker. So we will be sharing with another payload that's flying up, CubeLab.
Okay, well, this will conclude our demonstration, and our next televised event will be the NASA Aeronautics Research Update at 8:15 a.m. tomorrow morning. For more information on the STS-135 mission and crew, go to www.nasa.gov/shuttle. Thank you for joining us.